Good morning. Today we are going to go uh, through paper 5, okay, for the May-June 2023, okay, variant 51. Okay, we are going to comprehensively solve this paper. Okay, so let us get going. So the first question says that a wooden cube of mass A is placed on an inclined plane. The cube is attached to a cylinder mass B using string that passes over a pulley as shown. So we have a cube with a mass A and a cylinder with mass A. This is mass B. Okay. The angle between the plane and the horizontal surface is theta. Initially, the cylinder is held at rest. So it is telling us this is an angle theta and the system is kept at rest. The cylinder is released. The time for the cylinder to fall a distance d is t. Okay. Then we have falling distance. Let us say this is the distance he's mentioning, which is the distance between the end of the cylinder and the surface. This is the distance, sorry. D. Okay. And we are measuring the time it takes the cylinder or the system to fall this distance. Okay. So we have D, theta, D, and T. Okay. Now he's telling us it is suggested that T is related to theta by the relationship, and he's giving us this equation, okay, where H and K are constants. Plan a laboratory experiment to test the relationship between theta or T and theta. Then one of those two values or variables, one is going to be the dependent variable and the other is the independent variable. Okay, he's not telling us which is which, but we have to decide for ourselves. So as the problem goes, or as the experimenter goes, okay, you are getting an angle theta, okay, or you are fixing the plane at the inclined plane at an angle theta, and you are setting the cylinder to a height h as indicated over here. Okay, then you are making it fall constant or fall this distance, and you are measuring the time. You are measuring the time it takes it to fall this distance. Okay, then from here we can see that we can vary theta and measure the corresponding time it takes to fall the distance t. Then from here we can see that theta is the independent variable, t is the dependent variable. Okay, this is what we learn from here. We have two values, h and k are just constants. H and k are constants. We need, or the experiment needs to calculate. Okay. So he asks us, in your plan, you should include or we should describe a procedure to be followed, the measurement to be taken, the control of variables, the analysis of data, any safety precautions. To carry out an experiment to investigate, okay, the relation between T and theta, and how can we get the values of H and K. Okay, the way to go through this experiment, okay, or this kind of questions, try to write all the variables that you have. We have theta, we have T, we have H, we have K, okay, we have A, we have B, and we have D. Okay, now we say which is which. For theta, it is going to be the dependent variable. T is the independent, sorry, the other way around. This is the independent variable. This is the dependent variable, constant to be calculated, constant to be calculated, a mass of, what is the mass of cube? Mass of cylinder, height of cylinder. Okay, then what we are going to do, we are going to make a small sketch diagram to tell how we are going to calculate the height D. Okay, and the sketch is very simple. This is how the sketch looks like. This is the plane. Okay, we have here the cube. Okay, and we have a small let me okay, we have okay, this is a cylinder. Sorry. This is the cylinder, and this is the distance D. D. How we are going to measure? We are going to use a meter ruler. D. We are going to use a meter ruler like this. Okay, to measure the height D. Okay. Now remember that as the scenario goes, the height D is also constant. What we are going to vary? We are going to vary the angle theta. We are going to vary the angle theta, adjust the height of the cylinder to be always be D. Okay, where you're going to use the meter ruler, or we are going to make a mark somehow over here. Okay, we are going to fix this height as always to be D. Okay, then we allow it to free fall, and we measure the time it takes to fall this fixed distance of D. So how we are going to proceed? This is how we are going to answer this question. Number one, set the experiment as shown in the figure above. Okay. Now we are going to tell him how we are going to measure the values, all those values. How we are going to measure A, B, and D. Okay, and those are the control variables. Those are the variables that we are going to keep constant throughout our experiment. Okay, for the mass of the cube and mass of the cylinder, we are going to use a digital balance. Say use a digital balance to measure the mass of the cube A and the mass of the cylinder B. Okay, so we are going to use a digital balance to take the mass of A and B. 3. Another control variable is D. Using a meter rule fixed parallel to the cylinder as shown in the figure, set or mark a fixed distance D above the bench. 4. This is important. For each value of A, B, and D, take 2 readings and use the average. What does this mean? That for the value of A, we take 2 readings. For B, we take 2 readings. For D, we take 2 readings. Then we calculate the average value for A and B and C and D. And these are the values that we are going to use later on. Number 5. Number 5. Now the experiment is already set. Okay, and everything is fixed. Using release the masses and allow them to fall freely. Okay. 6. Using a stop watch. Using a stopwatch, measure the time the cylinder takes to fall the distance d. Okay, then you are going to use a stopwatch. You are going to release, or this is what we are saying. We are going to let the cylinder now falls freely. Then it is going to move. Also, the cube is going to move. It is going to fall a distance d. Time this the falling time, okay, and call it t. This time is t. Okay. 7. For each theta, or let this we keep it for later, or let us say it. For each theta, take two values for t and calculate the average. Okay, so for each value of theta, okay, we take two values of t. We repeat the same measurement twice. Then we calculate the average to be t, and then we are going to put it in the table. Okay. 8. Change the angle theta. Adjust the cylinder as to be at the fixed height d above the bench. So we are going to use another angle theta. Okay, now if we change theta, then we are going to readjust the position of the cylinder such that it will always be at a fixed height d. Again, d is always going to be fixed. Okay. Nine. Take 6 sets of values for theta and the corresponding times t. Record your measurements in the table below. Okay, then we are going to have this table. We know that we are going to measure it to vary the angle theta. It is in degrees. We are measuring the time t in seconds. Okay, now let us go back to the equation. Let us have a look at the equation. This is the equation. What we are going to do, we know that we are going to use t as a dependent variable and theta as the independent variable. So let us reorganize this equation to be or to look like an equation of a straight line. How it is going to look like? Okay, it's going to be something like this. 1 over t squared is equal minus a h O divided by 2d a plus b sine theta minus ka divide 2d a plus b. Okay, remember that the equation of a straight line is y is equal mx plus c. So this is this is the dependent variable. This is the independent variable. This is the gradient, and this is the intercept. Okay. Now, if we make a plot of 1 over t squared times sine theta on the x-axis, okay, we should get a straight line. This straight line got a slope of minus ah over 2d, a plus b, and an intercept of minus k divide 2d, a plus b. Okay, so we have to complete the table. We have sine theta. We don't have units for sine theta. And we have 1 over t squared and the unit s minus 2 or seconds minus 2. So this is how our table going to look like. Okay. Now, step number 10. Make a graph plot of sine theta x-axis and 1 over t squared y-axis. Okay. Now we write this equation. A straight line is expected having an equation 1 over t squared is equal minus a divide 2d a plus b sine theta minus ka 2d a plus b. Okay, we say that the gradient is equal minus a divide 2d a plus b. Okay, sorry, we have an h over here. Okay, the intercept is equal minus ka divide 2d a plus b. Okay, he is asking us how to calculate k. Here we have h. How to calculate h and k. He asks us how to calculate h and k. So we can use this equation. Can use this equation to calculate h, and we can use this equation to calculate k. Therefore, h H is equal minus gradient or 2 gradient times d A plus B divide A. Okay, this is H, and K is equal 2D minus 2D intercept times intercept times A plus B divide A. Okay, okay, I think this is what we are having. So we answered all these questions. The procedure, we describe the procedure, the measurements to be taken, the control variables, which variable we are going to keep constant, which variable we are going to vary, the analysis of the data, what we are going to do with the data. Now, any safety precaution to be taken. So, one of the precautions that we should make sure that make sure the mass system moves freely. 2, make sure to always adjust the distance or the height d as needed. 3, make sure to time to measure the falling time for just before the cylinder hits the bench. 4, use large height d as much as possible to reduce measurement errors. Okay, I think we are good with question number 1. Okay, let us proceed with question number 2. A student investigates the discharge of capacitors in the circuit shown. Okay, the capacitors have capacitance Cp and Cq. So we have two capacitors, Cp and Cq. The student closes the switch to charge the capacitors and then records the maximum reading V naught on the voltmeter. The switch is open and a stopwatch is started. the capacitor discharges through the resistor and the reading on the voltmeter decreases. When the reading on the voltmeter is T, the time T is recorded. The discharge of the capacitor is repeated and the mean time T is calculated. Okay, the experiment is repeated for different values of Cp and Cq. For each combination of Cp and Cq, the combined capacitance C is calculated. Okay, it is suggested that C and T are related by the equation. So he told us that C and T are the dependent and independent variables. One of them is the dependent and one of them is the independent. So the one that we can control is C, then it is going to be C is the independent. This one we can control ourselves. Okay, and we can calculate. T is the one that we measure. So it is going to be the dependent variable. Okay. Now V and V naught are fixed values. Okay, they are constant. He told us they are fixed values. Okay. So now again he told us a graph is plotted of T on the y-axis and again C on the x-axis. So whatsoever we plot on the x-axis is going to be the independent variable. Okay, and what we usually plot on the y-axis is the dependent variable. Determine an expression for the gradient. Determine an expression for the gradient. So we have to write this equation to look like an equation of a straight line. Okay, so we have T ln V minus V naught is equal minus T over CR. So how we are going to order it? It is T minus CR ln V over V naught. This looks like the equation of Y is equal M X. Okay, let me write it this way. Minus C. Okay, so this is the independent part, the dependent part. This is the independent part, and this is the gradient. Okay, so what is the gradient? It is going to be minus R ln V divide V naught. Okay, this is going to be the gradient. We don't have an intercept because there's nothing over here. The intercept is going to be 0. Now, he told us he's giving us a values for Cp and Cq. We are getting values for Cp and Cq. And he told us that we need to complete this table to have C. And he's telling us this is how to calculate C. C is equal Cp times Cq divided by Cp plus Cq. Okay. So let us do the calculation. Okay. Doing one for you. Let us get our calculator. This is our calculator. Okay. So it is the multiplication divide the addition. So it is 2.2 times 1.5 divide 2.2 plus 1.5. Okay, we are getting 0.891891, so on and so off. Okay, so what I'm going to report is 0.892. 0.892. So why did I write it like this? Remember, we need to check the significant figures. So how many significant figures do we have here? We have two significant figures. How many significant figures do we have here? We have two significant figures over here. So in the calculated value for C, it is accepted to report the values to either two significant figures or one extra significant figure, three significant figure. So it is either two significant figures or three. We decided to go for three significant figures. The choice is ours. If you report it as 0.89, it is going to be okay. Two significant figures, two significant figures, two significant figures here. It is fine. If you go for one extra significant figure, you are also good. But don't get more significant figures like 4 or 5. Only either two significant figures or three, one extra. Okay. We go through and carry out the whole rest of the calculations. So here it is 1.32, 1.58, 1.03, 1.18, 2.08. Okay. Now he is telling us includes absolute uncertainties in T. Okay, includes absolute uncertainties in T. So how do we calculate the absolute uncertainties? I'm going to tell you how to do that. Okay. First, so he took two values or two measurement for T and then calculated the average. So let us do the average values. It is 12.9 plus 14.5 divide 2, 13.7. Okay, I'm going to do the average first. Okay, now we are going to do what? Calculate the absolute uncertainties. Okay, so if we have two values, how to calculate the absolute uncertainty? It is simple. What I'm going to do now, it is the maximum minus the minimum, or one minus the other. Max minus minimum, and I'm going to divide by 2. Maximum minus minimum divide by 2. So how to do it? This one is going to be, this first one is going to be 14.5 minus 12.9 divide 2. This one is going to be 21.1 minus 19.7 divide by 2. This one is going to be 24.9 minus 23.7 divide 2. Okay, let me do one for you. So the first one is going to be 14.5 minus 12.9 divide 2. It is 0.8. So it is plus or minus 0. So let us start making the graph plot. And he is asking us Draw the straight line of best fit and a worst acceptable straight line on your graph. Label both lines. Sorry. He is telling us plot a graph of t against c, 10 to the power minus 4, include error bars in t. So we are going to have error bars in the y-axis. Okay, let us start with the first value. It is 0.82 and 13.7. Okay, now let us have a look or investigate the x-axis or the scale on the x-axis. So each square is 0.2 10 to the power minus 4 farad. Okay, then each small square is 0.2 divide 10 equals 0.02. Okay, now each on the y-axis, each big square is 2 seconds, right? So one small square is 0.2 seconds. 0.2 what? Seconds. Okay, this is good. Now we know this information. This is 0.02 and this is 0.2. Now we have 0.89, 0.8. This is 0.8. Okay. 0.82, 0.84, 0.86, 0.88, 0.9. Okay. So it is 0.9 over here, and we have 0.80, 0.88, and we have 0.9. Okay, between 0.88 and 0.9. So the variance value on the x-axis is going to be somehow around this point, around this point. Okay, it is going to be around here. So what is the y? Okay, let us do the calculation. So it is 12. This one is going to be 30, 13.2, 13.4, 13.6, 13.8. So the value is going to be somewhere over here. Okay. Now we are going to go for the error bars. So the error bars, this is how we are going to do them. 13.7, okay, plus 0.8. It is going to be 14.5. And we have 13.7 minus 0.8. We are getting 12.9. So the error bars are going to expand from 14.5 to 12.9. So this is 12, right? This is 12.8. This is 13. Then this is 12.9. Okay. Where is 14.5? This is 14, 14.2, 14.4, 14.6. Then in the middle here is 14.5. Well, I'm doing it like this so that you can follow with me. 2, 4, 6. So it is over here. So this is the first one. Now we go to the next. It is 1.32, okay, and 20.4. So 1.32 is 1.2, 1.3, this is 1.3, this is 1.32, okay, and we have 20.4, 20.4, 20.2, 20.4. So it is over here. It's an easy one. Okay. Now, what do we do for the error bars? We have 20.4 plus 0.7. It is going to be 21.1. And we have 20.4 minus 0.7. What is going to be 19.7. Okay, so it goes down to 19.7 and up to 21.1. So where is 19.4? 19.7? This is 19, right? This is 19. 19.2, 19.4, 19.6. This is 19.7 in the middle. Okay, it goes to 21.1. So this is 21 and this is 21.1. Okay, and this is our error bar. Now we go and carry out the remaining ones. We have 1.58, 1.58, and 24.3. So one is 0.58, 1.5, 1.5. This is 1.5. This is 1.58. It's 1.58. This is 24.2. So 24.3 is somewhere here. Yes. Okay. Now the error bars. 24, 24, oops. 24.3 plus 0.6 is equal to 24.9. We have 24.3 minus 0.6. We have 23.7. Okay, so it goes to 24.9 and down to 23.7. So this is 24.4, 0.6, 0.8. This is 23.9 here. Okay, 24.9, 23.7. It is here. 6, 8. No. 2, 4, 6. Yes, here. One point oh three. 1.03, we have to go back, right? 1.03. It's somewhere here. This is 1.1. It's 1.2. 1.03 is over here. So 1.03 and 16.1 and 16.1. So 1.03 is almost 1. Okay, and 16.1, it is here. Okay, the error bar is 0.8, so it goes to 16.9 and down to 15.3. 15.3, yes, goes down to 15.3. This is 15.2. This is 15.3 and 16.9. 16.9. Here it is. Okay, and here is the error bar. Now we have 1.18. 1.18. 1. This is 1.1. 1.8 is here. Okay, and we have 18.3. So this is 18, 18.2, 18.4. We have 18.3 over here. Okay, now it goes to 19 and 17.6. 17.6 is down here. 17, 2, 4, 6. Okay, and it goes to 19, right? 19, yeah. Okay, now we have 2.08. Where is 2? 2 is here. Okay, 2.2. 2.02, 2.04, 2.06, 2.08. Yes, 2.28. Yeah, let's mark it here. And we have 31.5. Yes, this is 31. Is 31. 31.2, 0.4. Here's 31.8. Sorry. Two, 4. Okay, here. Okay. And the error bars is 32.1 and 30.9. 32.1. Okay, this 31, 31.5 plus 0.6 is 32.1, and 31.5 minus 0.6 is equal to 30.9. Okay, so this is 30.9 over here. Okay, and this is 32.1 over here. Okay, and here is the error bar. I think we are now good with our plot. Now we use our meter ruler to get a good line that passes through all the points, and we hopefully they pass through the origin, okay, as much as possible. So I'm going to make a, unfortunately you cannot see me with my meter ruler trying to get the best line, but okay, we cannot. So this is going to be our best fit line. It is marked in green. This is the best fit line. Best. So you know it. This is the best fit line. It's going to be green. The other line, I'm going to mark it as a dashed line. Okay. Now we were asked to make two graph lines, or two straight lines. One is the best fit line, and one is the worst or the steepest or the shallowest line. Okay. So the shallowest or the steepest, doesn't matter which one we are going to use. It's going to be this one. We also try to make it, okay, go through all data lines, but it is going to be the shallowest that we can get. So I am making it in a dotted line, and the best fit one is going to be the straight line. Okay, so the dashed, I'm going to call it the worst fit line. Doesn't show up nice. Worst fit line. Okay, we are going to calculate the slope for both lines. What you are going to do, you are going to draw two right angle triangles. Draw two right angle triangles. Okay, one for the green or the best fit line, and one for the worst fit line, like this. For example, sorry. No, still not getting there. Something like this. Okay, and calculate the gradient. So the gradient I'm going to use for the best fit line, I'm going to say the best fit, I found the gradient of 30.2 minus 14 divide 2 minus 0.92. If I do the math, it's going to get 15 times 10 to the 4 second per farad. Remember, from where did I get this 10 to the 4? It is from here, minus 4. Okay. Now, the worst fit line, it is going to be 29.6 minus 14 divide 2 minus 0.88 times 10 to the power minus 4. 13.93 times 10 to the power 4 s farad. Sure, you can get different results, right? Definitely are not going to get exactly my values or my straight lines, but it's going to be very close to those values. They are going to be different, but not very far away from this. Okay. Now, which gradient should we use? Okay. We are going to calculate the average. We are going to calculate what? Sorry. We are going to report the best fit gradient. It's going to be 15. How can we calculate the uncertainty or the absolute uncertainty? The absolute uncertainty is best fit minus worst fit. Okay. And we ignore the sign. Best fit minus worst fit. What is the best fit value? It is 15 minus 13.93. Okay, do the math. 15 minus 13.93. 1.07. Okay. Always we are going to keep the absolute uncertainty to one significant figure. We always keep the uncertainty or the absolute uncertainty to one significant figure. Then we are going to say it is plus or minus 1. Okay. And we are going to quote the 10 to the power 4 s second and farad. Make sure that the value you quote here have the same decimal number of decimal places as the uncertainty. Note, make sure the value or the gradient or the value whatsoever it is measured value have the same number of decimal places as the absolute uncertainty. Okay. Note, always quote the absolute uncertainty as one significant figure. Okay. So now we are done. We got 15 plus or minus 1, 10 to the 4. The values of V0 and VR, we are given those values. Calculate ln V over V naught. Includes the absolute uncertainty in ln V over V naught. Okay, let us first calculate ln V over V naught. So it is going to be ln V is 2.4 and V naught is 4.8. Okay, we do the math. So it is natural logarithm or ln 2.4 divide 4.8. I think it is 0.693, 0.69 minus 0.693 is equal minus 0.693. Okay, and doesn't have any units. Now includes the absolute uncertainty in ln. Okay, as we said before, to calculate the uncertainty in the ln, it is going to be the ln of the average value minus ln of the maximum. Okay, what is the ln of the average value? It is ln of the given values. 2.4 divide 4.8 minus. What is ln of the maximum? The ln of the maximum is calculated as follows. It is the maximum of the numerator divide the minimum of the numerator. Maximum of the denominator divided by the minimum of the numerator. Okay, so it is going to be 2.4 plus 0.1. Okay, divide 4.8 minus 0.1. Okay, and we get the absolute value. What does the absolute value means? That we don't care if we got a minus sign. If this value is minus or positive, we don't care. We always quote the positive value. Okay, so let us do the calculation. We know this part is minus 0.693. This part is going minus ln 2. So it is ln 2.5 divide 4.7. Ln 2.5 divide 4.7 equal minus 6.321 minus 0.6 minus 6 point let me see how much. Sorry, 0.631. 0.631. Okay, 631. We calculate the difference. Okay, it is 0.6393 minus 0.631. This 0.062. Okay, now we are going to report it to one significant figure. We are going to report the uncertainty to one significant figure. So it is plus or minus 0.06. Okay, and what is the value over here? We are going to quote it to the same number of decimal places. So it is 0.6 0.69. Okay, and we have a minus sign. We have to remember this. Using your answer to A and C and D determines the value of R. Include an appropriate unit. So, what do we have? How is R related to anything? This is R. R is related to the gradient. Okay, so the gradient is equal minus R ln V over V naught. Okay, so therefore R equal minus gradient, okay, ln divide ln V divide V naught. So what is the gradient? The gradient is 15. Okay, the gradient is 15. Then it is equal, then R is equal minus 15. This is the minus, divide minus 0.69 times 10 to the 4, right? Then it is 21.74 10 to the 4 SF. Okay, so R is 21.74 times 10 to the 4 second farad. Okay, this is what we got. Determine the percentage uncertainty in R. Determines the percentage uncertainty in R. So we go back to this equation. R is minus the gradient, divide ln V minus V naught. So we always remember that the percentage uncertainty for two values that are divided together is equal. So let me write the equation here. If we have A is equal B divide C, or A is equal B times C for any one of them, the percentage uncertainty delta A over A is equal delta B over B plus delta C over C for both of them. Remember this. This is what we have discussed before. So it is going to be delta R divide R is equal delta gradient divide gradient plus delta ln V divide V naught over ln V divide V naught. We know the delta gradient. We have calculated before. We know the gradient. So the gradient, delta gradient was 1. The gradient was 15. Delta ln V naught, we did calculate before. It is 0.06. Divide 0.69. And we multiply definitely by 100 to get the percentage uncertainty. We do the calculation. So it is 1 divide 15 plus 0.06 divide 0.69 times 100. It is 15.3%. Okay, 15.3%. Now he's telling us the experiment is repeated. Determine the value of C that gives a value of T is equal to 60 seconds. Includes the absolute uncertainty in your answer. Include the absolute uncertainty in your answer. So what do we have? Uh, the experiment is repeated. Determine the value of C that gives. Okay, we have T is equal minus R ln V over V naught. Okay, C. This is the gradient, right? Is the gradient. So T is equal MC. Okay. Therefore, C is equal T over the gradient M. Okay, we are given C as 60. Divide the gradient is 15. Okay. Uh, times 10 to the 4. It is going to be 4 times 10 to the power minus 4 farads. Okay. Then it is 4. And he is asking to include the absolute uncertainty. Okay, how do I calculate the absolute uncertainty? It is going to be delta C divide C is equal delta T divide T plus delta gradient divide gradient. Okay, therefore delta C is equal delta C delta T over T plus delta gradient over gradient times C. Okay, let us substitute. So delta T, you are free to choose. Okay, what is delta T in this case? You can choose that delta T is 0 and this should be fine. But for us, we can decide that delta T is 0.1 second. It is a minimum value or the least significant or 1 unit of the least significant value of the quoted result. So delta T, delta C is equal 0.1 second divided by 60 plus delta gradient is 1 over 15, okay, times C, which is 4 times 10 to the power minus 4. Okay, now we do the calculation. So it is 0.1 divide 60 plus 1 divide 15, okay, times 4.273, and we quote it to one significant figure, then it is 0.3 plus minus 0.3 times 10 to the power minus 4, and we keep this value to the same number of decimal places as the absolute uncertainty, so we quote it like 4.0, as this is the final result. Okay, this is the final result. I think we are kind of done with this paper. Okay, please have a good look at it. It should be simple. The more you solve past exam paper, the better you get and the faster you get. Okay, the exam time is very tight, so you need to be cautious and you have to be very cautious while going through the paper. Okay, good luck. Cheers.